Hello everybody. This presentation is an introduction of signal processing through fun videos which I have created. My name is Dhanesh Chikurup. I am from Amrita Vishwa Vidyapeetham, Bangalore campus. So before going into the subject, I would like to show you a small video which I have downloaded by the way from the internet. So what was this video about? This is about signal processing happening inside human anatomy all the time, by the way. As we know, we humans process signals, and once again I will try to show you this video.
Ouch! Gotcha! Pain.
So what really happened? A fly came and sat on Adam's nose. So these there are sensory tissues on the tip of the nose. So it relayed the information to the brain, some danger, I am feeling irritant, and so on. That information is passed to the brain. Brain processed this information and relayed a signal back. Where? Not to the nose, to the hands. And hands took a handsome action and killed the fly. Okay? So this is an interesting example of signal processing happening inside human body all the time. Our eyes are continuously processing visual data, visual signals, nose, smell, and so on. And this information is 24/7 processed, maybe except in deep sleep, right? So this is what is, so signal processing is happening in the body all the time. And just like cameras you have in video cameras and mobile phone and so on, your eyes are the lens of the human camera. Our nervous system carries information to the brain. Brain processes the signal. So our body is actually a signal processor with a lot of sensors attached. What a wonderful creation, isn't it? So we will go to the next slide. This slide is about a digitally modulated signal. What is a digitally modulated signal? A high frequency carrier is there, as you can see, this the sinusoid, which is very high frequency, and the amplitude and phase of the sinusoid is continuously changed according to the information. In this case, the information is a 16 QAM baseband signal. So I'm not going, how can you understand this? It's actually, see, these two parallel streams of data is there. This is called the in-phase channel and this is called the quadrature channel. According to the changes in the in-phase channel I, the first one, and the second one, which is the Q channel, the phase and amplitude of the carrier changes. At the receiver side, you will track the changes and you will build up this I and Q signals. Okay, so reverse process will happen in the receiver. While transmitting, we send a high frequency carrier to the receiver. So receiver will receive this and convert it back into I and Q signals. And in fact, these I and Q signals are generated from binary stream of data. Okay? So for example, nowadays everything is coded in digital form or binary form as zeros and ones. So this I and Q signals changes according to the zeros and ones, and this I and Q modulate this high frequency carrier, and this is the digitally modulated signal. And in real time, how it looks like, I'm going to play this video. As you can see, with time, the data changes, the binary data changes. When the binary data changes, the I and Q channels changes. You see, the I is the top one, Q is the top one. And the changes in I and Q will change the phase and amplitude of the carrier. So that is how it works. So this is a digitally modulated signal. So this is another application of signal processing where signals are processed to produce a high frequency carrier. So as I have told you, signal processing is a very vast subject with a lot of applications, and it enables us to analyze noise due to vibrations in fighter aircrafts and seeking ways to cancel them in the headset of pilot. As you know, when the pilot flies, for example, a fighter aircraft, it's moving at supersonic speeds and very high frequency, and noise is created, and he will not be able to talk properly to the ground. So in these cases, we need to cancel this noise in real time. So signal processing helps us. Similarly, signal processing enables us to clean up sensor data. It enables wireless communication, biomedical applications such as ECG, EEG, image processing, and so on. Okay, I'll go to the next slide. So without going into much mathematics, I would like to present Fourier series. What's a Fourier series? Fourier series essentially enables us to represent periodic signals as sum of sinusoidal signals. It's interesting, right? Any periodic signal can be converted into sum of sinusoidal signals. So who made this contribution into the world of engineering, science, and so on? Fourier. So Fourier, so this series, as you know, as it is known as Fourier series, it's an infinite series of sinusoidal signal. No matter what the shape of the periodic signal, you can always represent that periodic signal as a sum of sinusoidal signal. And it's interesting to note that the more the number of components in the series, better will be the approximation. The components here is nothing but the sinusoidal signal. So the more the number of sinusoidal, better the approximation. So this video illustrates this. As you see, the number of sinusoids keep on increasing as a result. So now there are 17 components, now 19, 20. So it approximates very well the sawtooth waveform. So what is the lesson we learned here? We can represent even a sawtooth which has sharp edges in terms of sinusoidal signals. So the more the number of components in the series, the better the approximation. Now we see that with 44 or 45 sinusoids, it's almost like a sawtooth. So this is a very interesting contribution to signal processing. The Fourier series is a very important topic. So usually the course start with, any signal processing course start with Fourier series. And unfortunately there are, periodic signals is just, most of the signals are not periodic, okay? They are called aperiodic signal. Periodic signals and aperiodic signals, or aperiodic signals. The way you pronounce depends on where you are from, okay? So you must understand, so therefore you must understand what is the uh, condition for before you can apply Fourier series. The signal must be, of course, periodic. Okay, like in this case a sawtooth waveform. Now you can see I am approximating a square wave with Fourier series. Now there are 6 sinusoids, 8, 9. More the number of sinusoidal components in the series, the better the approximation. And with 17 sinusoids, you can see that it is almost like a square wave. As the number of components increases, it's becoming more and more like an exact square wave. So that is the application of Fourier series. So Fourier series enables us to represent periodic signals using a series of sinusoidal signals. Now this is an introduction of Fourier transform. So what is Fourier transform? It enables us to represent a periodic signal. A periodic signal means there is no periodicity. In this case it's a rectangular pulse. We are finding the Fourier transform of a rectangular pulse. What do you learn from this animation? In the first picture on the top shows the rectangular pulse in time domain, and this is the magnitude spectrum of Fourier transform, left side, and on right side you can see the phase spectrum of Fourier transform. So Fourier transform enables us to translate a time domain, a periodic signal, into amplitude and phase spectrum. Okay, and interestingly, the independent component is frequency. So the spectrum means that is a function of frequency. Okay, so Fourier transform enables us to find the spectrum of a time domain, a periodic signal. And you can see, and what is the lesson we learned from this slide? The thicker the rectangular pulse, thinner the spectrum, which means the spectral components are very few for a thicker pulse. Okay, so high frequency components become smaller and smaller when the pulse becomes thicker. Okay, on vice versa, when this rectangular pulse become more and more thinner, it becomes thinner, the spectrum increases, spectral width increases, and phase spectrum is also shown on the right side. So the thicker the rectangular pulse, thinner the spectrum, thinner the rectangular pulse, thicker the spectrum. Okay, so this is a typical example of a noise. Okay, noise in engineering. So what? And noise always follow a probability distribution. That's a very important lesson we learned, right? Noise always follow a probability distribution, and mostly noise can be represented with a Gaussian as Gaussian noise, or a noise which follow Gaussian probability distribution. Gaussian distribution, by the way, is also known as normal distribution. So using a random number generator, I have created noise as a function of time. Okay, here x-axis is time or sample number. So as you can see that from the characteristics of the signal, it is quite random in nature. That is why it is called noise. So noise is always random. That's one lesson we learned from this animation. So noise is random, and noise always follow a probability distribution. In this case, it is Gaussian distribution. How can we say with surety that this noise which I have generated is a Gaussian distribution? The second picture illustrates that. What I have done. Amplitude of the noise is the x-axis in this picture. Amplitude of noise. Okay. And probability of occurrence is on the y-axis. Okay. For example, if suppose a random sample fall between, say, minus 0.25 and plus 0.25, the central bin will be added with a number, incremented with one, the counter will be incremented with one unit. Okay. Likewise, I have divided the entire x-axis into different bins, and if the noise voltage fall into that particular bin, a counter will be incremented, and that is why the height keep on increasing. Okay. And what do you see here? In the beginning, these rectangles were having the same height, and as the noise started building up, the central bin attains the maximum amplitude. Why? Okay, why the central bin? You can see the central bin is small in the beginning, but as time passes, the central bin has more and more voltages. Okay, so the reason why it is because the probability of 0 is more. That is why the central bin attains larger height. Similarly, the probability of higher voltages is smaller, and it follows like an exponential curve. Okay, you have studied in the textbooks that Gaussian or normal distribution is exponential. The reason is because of this. More chances that the distribution has a mean value. In this case, the mean value is 0. So more probability that the voltages are mean value. In this case, it is 0, as you have seen. That is why the central bin achieves the maximum height as time passes, and it is exponential. So Gaussian distribution is exponential in nature. I'll go to the next slide. And you have seen the earlier rectangular pulse, which is changing in width. Here is a rectangular pulse which is moving in time domain. Okay, moving in time domain. So what really happens? The amplitude spectrum is stationary, it's not changing. As you can see, the amplitude spectrum is constant because amplitude spectrum only depends on the width of the rectangular pulse. So, on the other hand, the phase spectrum, frequency versus phase, it keeps on changing. So, phase spectrum changes with the position of the rectangular pulse. So, Fourier transform has immense applications. You can examine the amplitude and phase of any aperiodic signal. That's the application of Fourier transform. Now, we are now ready to apply the techniques learned to answer few fundamental questions. Okay, these fundamental questions, by the way, every engineer is expected to know. Okay, so these two fundamental questions which we are going to ask ourselves are: explain scientifically why we need more bandwidth when the data rate is high. As you know, bandwidth is a scarce resource. People are fighting for bandwidth. As you know, when some frequency bands are released for civilian communication, so many operators fight to attain that bandwidth, right? There is bidding and so on, and government makes a lot of money. So bandwidth is a scarce resource. Military has reserved a lot of frequencies for their communication purpose. Similarly, satellite communications, ISRO for example, they have reserved a large bandwidth for their communication and applications. So we are supposed to know why larger data rate means more bandwidth. So what is data rate? Data rate means how fast we are sending the data. Okay, suppose we want to send a binary data of say 10101, 5 bits. If we send this 5 bits in 1 second or 5 bits in 5 seconds, which has more data rate? Sending 5 bits in 1 second means the bits are flying faster. Okay. So what is the consequence of having high data rate or sending the binary bits faster across a wireless channel or a wired channel? What is the consequence of that? The consequence is we need more bandwidth. Okay. So I am giving you the answer first. It requires more bandwidth to send larger data rate. So we are taking for nowadays for granted we are watching YouTube videos in our mobile phones and so on. If you want to have a very pleasant experience, video experience, of course, large amount of data should come to your phone in a shorter time, right? The consequence is larger data rate. So even more, so the larger data rate means what? We require more bandwidth. So this answer we will answer why we require more bandwidth. Okay. Now, next scientific question or an application which we deal with is, suppose a signal is noisy. How can we remove the noise from the signal and make it clean using Fourier techniques? So interestingly, the two mathematical techniques we have seen just now, namely some fundamentals of noise, Fourier transform and Fourier series. This is quite sufficient to answer these two questions, right? So we're going to see this in the next slide. This slide essentially explains why we need more bandwidth when data rate is high. As you see, I have how many bits here? 1, 2, 3, 4, 5, 6, 7, 8 bits are there. Okay, each bit is having 1 second. In the left side picture, I have for each bit 1 second. Okay. As a result, what is the data rate? 1 bit per second. So 1 BPS. Okay, as you know, in real life situations, we are Mbps. Okay, 50 Mbps. There is an operator who is providing 50 Mbps. There is another operator who is providing 1 Gbps. What does it mean? Gigabits per second. Okay, 10 to the power of 9 bits per second. So what it means is, suppose we have 1 gigabit per second. Okay, gigabit per second. Giga means 10 to the power of 9. So 10 to the power of 9 bits are transmitted in 1 second. What does it mean? It means that 1 bit has 1 nanosecond. Okay, that's the meaning of 1 gigabits per second. Just like 1 bits per second means 1 bit is sent in 1 second. 1 gigabits per second means 10 to the power of 9 bits are sent in 1 second. As a result, the thickness of the bit is substantially smaller than what you are seeing here. Okay, fine. Now you have in this picture 8 bits. As you see, they are random in nature. Okay, it keeps on changing. Okay, sometimes the first bit is high and it's a 1. When it's a 1, the amplitude is high, large. When it's 0, amplitude is smaller. So it's randomly changing. And you can see below, what is the spectrum? Okay, the spectrum is two-sided spectrum, Fourier transform spectrum is plotted. And as you can see, the frequency, it is focused near the 0 frequency. Okay, a lot of focus near 0 frequency. As it goes sideways, the amplitude of the signals or the spectrum is, amplitude spectrum becomes smaller and smaller. So we essentially learned that the spectrum is narrow here. And now you take another example here. In this case, one bit is having 0.25 seconds. Okay. Therefore, you can see that the 8 bits took only 2.5 seconds here on the right side here, and here you have 10 seconds. Okay, 8 bits took 10 seconds, whereas here it is approximately 2.5 seconds. And 1 bit is therefore the time duration for 1 bit must be smaller than 1 second on the left side, right? In this case, it is 0.25 seconds. Okay, so which means the right side picture has a larger data rate. You are able to you're sending more bits in 1 second. Why? Because the bit time is small. You are sending 4 bits per second. In the left side picture, we have 1 bits per second, and in the right side picture, we have 4 bits per second. The reason why it's 4 bits per second is because the time duration of 1 bit is 0.25 seconds. Now, what is the consequence of this when the time duration decreased or the data rate increased? Larger footprint of spectrum. So the more the data rate, the amplitude spectrum has become wider. As you can see here, all the energy is focused between -2 and +2. Here, it has gone to -4, +4, it's substantial amplitude. And it's random, because you can understand why the spectrum is changing, because the bits are changing randomly. In general, we can see that because of the larger data rate, we require more bandwidth. That is why if you want to communicate or process signals very fast, we need larger bandwidth. This is not just in the communications. For communications, it's also true for high-speed signal processors inside computers, okay, FPGAs and so on. So the larger the data rate, the larger speed, if you want to send a signal from point A to point B, we need larger data rate. The larger data rate translates to requirement of larger bandwidth. So the channels, transmission lines, wires and so on should support larger bandwidth. That is why you have special construction for your USB dongle. Okay, it transfer data very fast. So the construction of the cable for USB connection is special, because in order to support larger bandwidth, okay, it is sending signals very fast. Similarly, you can see that keyboard to computer, okay, you see a thin cable going there, and it supports a certain amount of bandwidth, because in keyboard activities are very slow. You press a keyboard key, it will take only fraction of a second, so it don't need to transmit data as fast as in USB. For example, you want to take a picture from the pen drive to computer, so you don't want to wait, right? So it requires larger speed of transfer, which means larger data rate. So larger data rate means larger bandwidth. Larger bandwidth means the engineering will become more challenging to handle larger bandwidth signals. And also larger bandwidth means since government hold the spectrum for wireless communication, so if somebody acquires larger bandwidth, so that particular operator has to pay more money. So therefore we can easily conclude that 5G requires more bandwidth than 4G. 4G requires more bandwidth than 3G, because why? The data rate is more for 5G compared to 4G, and data rate is more for 4G compared to 3G, and data rate is more compared to for 3G compared to 2G. Okay. So as the data rate increases, more and more bandwidth is required. So 5G requires more bandwidth because the data rate is very high. So in order to generate this two pictures, we only need Fourier transform. What we essentially do is, we do a Fourier transform of these bits, random bits. For example, we generate a bit combination, we have the time axis, we have the voltage, we just apply the Fourier transform integral, right? In book you will see an integral which explains the Fourier transform, which will enable you to find the amplitude spectrum of a given time domain signal. So that's all needed. Just fundamentals is required to understand this interesting question, which we face on a daily basis. Now, this is another example of Fourier transform. By the way, there is a tool called fast Fourier transform, which is there in MATLAB or a lot of open source tools where you can. So this FFT or fast Fourier transform. This is actually a tool for finding Fourier transform. You can use FFT to find the Fourier transform. So then why FFT? Why can't we resort to old integration and so on? Yes, this is a part and parcel of a computer tool. So why can't we just use it rather than sit and solve the questions, right? That is why. So FFT or fast Fourier transform is a tool for finding Fourier transform. Now, what is there in this? We have two signals. On the left side, you have a sinusoid. You see that? It's a sinusoid. It is peaking at, I have the fast Fourier transform signal. On the x-axis, I have the sample number in the fast Fourier transform, and the y-axis is the amplitude. Okay, I'm only plotting the amplitude spectrum of the FFT. So as you see, I have two peaks, which means it is single sinusoid. In FFT, if you have two peaks, means it is single sinusoid. Now, I'm going to add some noise into this signal. Okay, so this is the noise. So when I add noise into the signal, what will happen? The spectrum changes. Okay, the spectrum changes. Now what I'm trying to do is, I'm going to denoise it. I have only this signal. I will have this signal for fast Fourier transform of signal plus noise. I will do a technique called denoising. What I will essentially do is, I will remove the spectral components which are below a certain threshold. I have kept a threshold of minus 24 dB. When I remove the signals below the certain threshold, then what will happen? My signal becomes, my spectrum will become like this. That means so many components are removed. They were below minus 24 dB, so they were removed. So when I do an inverse fast Fourier transform, I will get the original signal. Original signal is supposed to be a sine wave, okay? But you see that because I kept a threshold of minus 24 dB, the signal which I retrieved after denoising is not looking like a sine wave. Okay. Now what I will do, in the next slide I will increase this threshold to minus 19 dB. When I increase the threshold to minus 19 dB, you see that the noisy spectrum is here. Okay, the noisy spectrum. And then we kept a threshold of minus 19 dB. Beyond the minus 19 dB, I removed all the components. And I do an inverse fast Fourier transform of the cleaned up signal for after applying the threshold. What will I get? I will get, it's much cleaner compared to, it's still not looking like a sine wave, but it's almost like a sine wave. At least the frequencies are very nicely captured. However, it's still some extra additional components are there. That is because of these two peaks on the sides. Okay. So minus 19 dB improved the retrieval of the signal. So retrieval signal is better compared to when the threshold was minus 24 dB. Once again, I would like to tell what is the threshold. You will always get a signal, corrupted signal, whose spectrum will always look like this. So in order to clean up the signal, what will you do? Below dB, below a certain dB, the threshold value, we remove the spectral components. And then we do an inverse pass Fourier transform. That is what is denoise. And in the next slide, we kept the threshold to minus 15 dB. As you see, when you kept minus 15 dB, the signal is almost like the original signal. So we are getting the sine wave back. So this is the principle of denoising. Now, my presentation is ending here, and this is not a complete course. This presentation is not a complete, there are a lot to learn, but I hope that this motivates the students to this interesting subject. We have seen two mathematical tools, namely Fourier series and Fourier transform. Fourier series enabled us to translate a periodic signal into sum of sinusoidal signals. Okay. The condition for applying Fourier series is the signal must be periodic. Then we have seen noisy signal. In noisy signal, we have seen that noise always follow a probability distribution, and I have illustrated, if you remember, a noise which follow Gaussian distribution, and you have seen that the probability distribution is exponential because of the fact that more chances is there for the noise to have a zero value or the mean value 0, and less and less probability that the noisy signal has high voltages. So as a result, the probability distribution becomes Gaussian or a bell-shaped curve. And after that, we have understood how more data rate means more bandwidth is required. More data rate means more bandwidth. Okay, and then we have seen the process of denoising. Thank you for listening.